Right. It's my pleasure to welcome you all to the fourth day of the Applications-Driven Coding Workshop. This morning, we're going to hear from Eitan Yaakobi first about DNA storage. It's great to have him. We overlap UC San Diego, so I'm very happy with this. And also, as you know, he's at the Technion. I think in some sense, he's really taken this direction and covered all the bases of DNA, right? You guys are now doing experiments. Yeah, but they're doing experiments and really understanding the application itself, right? So, which is a perfect fit for this conference.
Great. Thank you for the introduction, Henry. Thank you for coming. I'll not do the repetition for the organizers, but I will raise the question. We were wondering all of the workshop, the partition of the amount of time per talks. So some talks are 25, 30, or 40. So it's a question which we are still not be able to figure it out. So, but when I saw the program, I saw that I'm going to be the first speaker on the fourth day. And then I thought to myself, wow, that's great. If it were ISIT, it means that I would get the Shannon lecture. So I would... wishful thinking, I guess. But then I said, okay, if I want to prepare a Shannon lecture, what should I do? So it's very simple nowadays. What do? You go to ChatGPT. So I went to ChatGPT to prepare a Shannon lecture. And then ChatGPT told me, you're so old. Rudy was already there before you. He prepared his own lecture. Go figure out your own lecture on your own. So I figured I should stick to what I wanted to do. And if I ever dream about something like this, I should do some more papers before that. So. Great. So this is a joint work with Daniela Barlev and Omer Tabari, who are PhD students in my group, together with Ryan Gabris, who was here all week, and then he disappeared from my talk right on time. And Anina Guica and Alberto Ravagnani from Eindhoven University of Technology. And maybe the title, Henry gave me already the beginning of this, so cover your bases. And what we're trying to do is to really see what it means to store data in DNA. And there are many challenges, both from the coding and also from the synthetic or the biology side of this. And sometimes many times I've been asked, is it really going to happen? Or, give me the motivation and so on. So I prepared some slides for you so you can see the motivation for DNA storage. So here's motivation. You saw the motivation. This is good. I'm skipping the application, everything. If you really want to see that, we gave a tutorial last ISIT. It's not online, but if you really want to see it and get all the background on DNA and so on, send me an email. I'll send you the link to the recording. It's like 3 hours, and we try to cover the basics of this and many of the theoretical problems on that. I will say that whether it is or it's not going to happen, I'm not be able to predict. But what I can say is that there are enough people who spend a lot of time, but more than that, spend a lot of money to really check the possibility to have a storage system which is based on DNA. Olgitsa is not here, but she's one of the pioneers working in this area for, I think, over 10 years already. And there are many companies. Maybe I can go back to this slide. So this is some of the companies. So Twist, it's a biotechnology company that they are making printers just to really print synthetic DNA. So they can make any DNA sequence, almost any DNA sequence that you want. Some of the other companies over here are mostly startups, what they want to do is DNA storage. There is also the DNA Storage Alliance, which is a group of bunch of companies, and also research group, which they're trying to work together on this exciting area. Okay, so this is but what I can tell you now is to give you the introduction for DNA storage, and maybe I'll spend, yeah.
So when you say you can make any DNA sequence, do you mean any sequence of GCAT, or what is the meaning of any DNA?
Yeah. Okay, so give me a few more minutes and we'll get to that. So I don't know biology, but what I know is that we have A, C, G, and T. That's the amount of biology that we need to know. And we also have what we call DNA strand, oligonucleotide, oligo, whatever. It's a string. Instead of zeros and one, now we have A, C, and G, and T. This is great. Now we can arbitrarily decide that A corresponds to 0, 0, and so on. So if I'm getting some binary string, I can convert everything to this A, C, G, T. Wonderful. This is great. Now we know that in our human body, we have roughly in every cell 3.5 billions of this DNA strings. It's not one long string. It depends on the genes and the chromosomes. But you can generate basically in the nature roughly over like 200 millions of bases, like in one long string. Today, you can also generate, in the corresponding to your question, like a string of DNA. It's a DNA printer, and maybe I have the picture. Yeah, this is a printer of DNA. Here you have ink for A, this is C, this is G, T, and so on. So you talk to these companies, and then you ask them, hey, make me, what do they have over here? I want to have A, C, T, A, G, and they say, no problem, pay me a lot of money, and we'll make you whatever you want. But I cannot make something which is the order of millions of bases. We can make something much more modest, 200 bases, roughly. What you can do with 200 bases, basically nothing, but we still want to be able to store something. Good, so let's see how it works. So this is the picture of how the DNA storage system would look like. And there are two main processes. So one is the DNA synthesis, and the other one DNA sequencing. So synthesis is really to the writing stage. And I have my file. I can convert everything to this DNA strands. Now we have this printer, DNA. Everything is in vitro. So no living organism, no bacteria. Everything is just synthetic DNA, which we get a powder of the DNA, and we store in a tube with some water. Very simple. Sequencing is the process of reading DNA. And we're going to have another talk this afternoon. So looking forward. But I'll get into the sequencing, but this is the main topic theoretically of what I want to do. So this is the two main processes that we have here. Now I said that we do have a strong constraint. When we talk to these companies, they tell you, sure, no problem, but we can make roughly 200, 300, 1,000. You cannot do more than that. But so I can, instead of making one strand, I can make many of them. So sure, no problem. So I have a file, and I'm going to break it into many DNA strands. I talk to this company, and then they're going to make it. When they make it, they don't make you just one copy per strand. You're going to get, like, I wrote here thousands, but it's actually millions or even billions of copies of this DNA strand, which everything is going to be over here, kind of like a big noodle soup that we're going to have.
So
yes,
they're all cut at different, these whatever 1,000 copies of the same thing. They're all cut at different positions, or they're all 200 long, the same.
Same thing, yeah, same thing. So here I have my file. I'm going to convert it into this. Everything here say 200. From this, I'm going to have millions of copies. Same one, repetition code.
So, and it's not possible that they break at different things because.
No. It's not like the sequencing, shotgun sequencing, that you have a long sequence and then you break it. I mean, here we start with something very small. So you don't need to do that. You have millions of copies only for this one, as is, with noise, clearly.
With writing, though, there are some errors. What's the error rate now?
I'll have some picture of this. Okay. Good. So now when I have a big file, I'm going to partition into many strands. So this is going to store the same, maybe I can store it in every strand, roughly 500 bits. So first 500 bits are going over here, and then it's going over here, and so on. Now, this is going to have millions of copies. This is also. So if I have a file, I'm doing my math, let's say that I need to have 10,000 strands that store the data, times, let's say, 1 million, it's a lot. All of this is here. Whenever I want to read, I'm not going to read the 10,000 times 1 million. We take a sample out of it, and hopefully we can decode and read the data back. Hopefully we'll see what that means, how do we do it, and also exactly how to do it also, what kind of machine. And again, Emanuele is going to talk about it in the afternoon, about the nanopore. Anyway, when we store everything is out of order. So we don't know that this is, if I'm going to read this one, I don't know this is strand number 1, this is strand number 2, and so on. So if I don't have a physical order, what I should do is put a logical order. So I'm going to put some of the bases here over here. Just tell me this is oligo strand number 1, 2, 3, 4, and so on. So if I'm reading and everything is noiseless, I know that this is strand number 1, 2, 3, and so on. I'm happy. I can recover the data. Everything is good. If you wonder what these guys over here, this primer, this is purely for PCR and also for sequencing, meaning there is no information over here. And it's more like a magnet. Whenever you want to read, there is an enzyme that will come and basically take this oligo that you want to read. And they're basically all the same. There are some works in which they don't have to be all the same. But basically for us, it's a meaning that zero information. It's only used for the biological processes for PCR and sequencing. So long story short, you have one file, you partition into many, many strands. Each strand is going to have millions of copies. Everything is going to be here. Whenever you want to read, it's impossible to read 10,000 times 1 million. We need to read maybe 100,000. So I'm going to take maybe let's say uniformly at random, out of the 10,000 times 1 million, 100,000 of them. And hopefully I get at least one representative for each one, and I'm happy to decode the data. Okay. Question so far? So if so far you got me, then you know how DNA storage works. I will say that there are some other attempts, some other approaches how to store data in DNA. Olgitsa had this really nice work about nicking in DNA, and there are some other composite DNA, and there are some other attempts how to do it. Also for the synthesis itself, it's not something which is, there is only one way to synthesize the DNA. Twist basically works a lot on it, and nowadays the synthesis process has to be very, very accurate. They don't use it for storage application, they use it like for a real application in which there is no, they don't have error correcting code, so there's no room for mistakes, and they're talking about 1 error per maybe 3,000 bases. Like it's, they're trying to get like to low error rate because they cannot put a code. But for us, errors is the butter and the bread. It's like, sure, I'm willing to do shitty synthesis, which is going to be low cost with high error rate, and then we're going to put all the fancy stuff that we like to do. And that's kind of like what the approach of the contribution from coding and information theory to this area. Good. So think that the 10,000 oligos are the points that we see here. This is the tube with the water, and now we're going to have many copies for each one of them. So I started with 10,000. Let's say I read 100,000 roughly. This is the picture that I see. Everything is noisy. Now, if I'm reading, for example, this oligo, I don't know exactly which one it belongs to because there is some noise, and the noise could also be in the address. So now it's a question: how do you do it? This basically we have the process of what we call clustering, grouping, binning. That you want to say all of this one came for oligo number 1, all of this one came for oligo number 2, and so on. How do you do it? Either you put an error correcting code on the address to be conservative, or you can say, you know, I have many of them here. Let me try to partition them based on similarity, how close they are to each other. But it's not Hamming distance. We have insertion, deletion, substitutions, so you have to do it with the edit distance. Sure, but or you can do some hybrid approaches how to do it. There are several solutions for this. It's a nice problem, which is not fully solved. Once I'm having all of this, now I can say here, oligo number 1, I have, say, 4 copies here. Now I'm trying to do sort of like majority. I'm trying to say what I think was stored over here, sort of like reconstruction, is something, and hopefully I'm doing that also error-free. But if I'm not able to do it error-free, now I have to apply an error correcting code. And that's basically the pipeline, how to do the readback. What we're doing over here, the decoding itself, these are the 3 main stages that you have. First, at the binning, clustering, then reconstruction, then whatever you want to correct errors using any kind of error correcting code that we have. Good. So we talk about errors in DNA, and we mentioned that you have deletions, insertions, substitutions, and this is some of the previous experiments that have been done. And referring to your question, Henry, I don't know if the errors came in synthesis or the error came in sequencing, because I know what I wrote, I know what I read. Whether the errors came during the writing or the reading, I don't necessarily know. And with this works also, this also depends. They use different technologies both for synthesis and also for sequencing. So Emmanuel will talk about the nanopore sequencing, which you get some signal and then you need to go back to the bases. And there is also the Illumina machines in which you read everything. You get the bases themselves. Illumina is much more reliable, more expensive. The nanopore much more less expensive, but less reliable. What you pay is what you get, as always. So you can see this is the error rates that based on like deletions, insertions, substitutions. This is, for example, per position. So sometimes you could also see per position what the error rates are. And many times I ask also the synthetic guys, I mean, why can't you make it longer? Like what's the issue? And really the way that the synthesis system works is that you take the bases one after the other. So if, for example, I want to synthesize, say, this oligo, it's not a printer that I get everything at once. It works with a cycle. So cycle number 1, I take some oligo, and I'm going to attach the base A. Done. Now cycle number 2, I need to attach base C. Done. Now cycle number 3, T, and so on and so on. And the longer the oligo is, the more difficult or more noisy it is to attach another base. So this is why they have to stop after 2 or 300. And that's okay, sure, but okay, now you take 1 200, another 200. But can you just put something together to attach them together? They gave me some other answers that I don't know what it means, but the answer is that it's not possible. But really, this is how it works, and this is why it's very expensive and very, very slow. If you want to synthesize, it takes hours to do it. like every cycle can be in the order of like several seconds. So if I want to synthesize a group of oligos together, I have a machine, and the machine would work with maybe, first cycle I can synthesize only A, then only C, and so on. And it's also a good question, how do you synthesize sequences which they are synthesize friendly, so it doesn't take a lot of time. Good. So this is this, and there are many coding problems over here, what I mentioned. So there's like clustering reconstruction, also constraint code. When you say like any sequence, so basically any sequence we can synthesize, but I mean, you don't want to have long homopolymers, run length constraint. We don't want to see, for example, 4 or more runs of A, C, G, or T. Sometimes they also talk about the GC content. So if we look at the oligo itself, we want to see how many G's and C's you have and how many A's and T's. So there has to be roughly balanced. It's not strictly balanced, but maybe between 40 to 60%. And this is not exact science. This is biology. So they tell you roughly, it should be, it's recommended, but it's not a hard constraint. You can still do that and things are likely to work, but maybe with more noise. And then again, there is the area of correcting insertion, deletions, and errors. Again, like there are many talks and many works on this. I'm not going to talk about the error correcting code. I want to talk about the sequencing itself. And again, I mentioned there are two approaches, either the Illumina machine or the one with the nanopore. And the nanopore, again, like it's Emmanuel will tell you exactly how it's amazing. Like it's a device roughly this size, which you can use for sequencing. And we also do experiment with that in my lab. Look, it's one of my students, Omer, like he built basically the lab, and we're able to, whenever we do experiment, we talk, for example, with Twist to synthesize DNA. We get it by FedEx, and then they do whatever. I don't know how it works. There is some flow cell. They put everything here. Then you get some signal, and then from the signal you get this ACGT and so on. And again, zoom in on this one, Emmanuel will in the afternoon. But what I want, and this is Omer. Okay, what I want to come back is to this picture here. And when I say, when I read this maybe 100, I started with 10,000 oligos, and I read 100,000 of them. And when I read it, it's sort of like you can think about it like one after the other. Usually it comes in batches of like several thousands, but I can think about it as a random process in which I'm going to read every time one copy out of the 10,000 that I have, say uniformly at random with repetitions, because I have many copies. So it's not like if I took one, I'm not going to be able to read it again. It has millions of copies. So for me, there is a process over here in which I'm going to read samples out of the oligos that we have with repetitions. It could also be noisy, but even without the noise, it's a good question by itself. And the problem is, I'm doing that until I'm telling you basically I'm done. So I think everything is noiseless. So I have 10,000 oligos. Each time I'm going to pick one of them uniformly at random. Whenever I hit all 10,000, I'm done. The sequencing process is over. And the question is, what is the expected, or the success probability also, but what is the expected number of reads until I'm able to decode my file? The problem is clear? Okay, so this is going to be the main focus of the rest of the talk. And I'll probably go over time, but we started 5 minutes late, so I'll try not too much. Good. So then the answer clearly depends on what kind of code you're going to use, also what the noise model, and also whether it's uniformly at random, or maybe there is some other distribution that maybe some oligos are more preferable to read over the other ones, and so on. Who knows the coupon collector problem? Okay, good. So if maybe you can already see the clear direction to the coupon collector problem. If you don't know it, then it's a really nice exercise, I think, to give it in any undergraduate class in probability. Then the problem started in failure in 1967. There is also the Dixie Cup problem. Next slide. But it's very simple. You have some cereal box, and every cereal box has a coupon. And now you buy the cereal boxes, say, to your kids, and they want to make sure that they get maybe all 100 coupons that you have. So every time you go, you buy a cereal box, then they open, they see the coupon, but they want to get all 100 of them. So the coupons are basically the oligos that we have. Reading one, it's buying the cereal box. And then the question is, what is really the expected number of cereal boxes that you need to buy until you're able to get all the coupons that you have? Good. So again, it's a really nice problem. It's not the answer is not too complicated either. I mean, when you buy the first one, you're happy. For sure, you're going to get a new coupon. All great. When you buy the second one, you're also very likely to get a new coupon, so not a waste. But if you got all 99 coupons now you want to get the 100 of them, then the success probability is 1 over 100. So on average, you have to buy 100 cereal boxes, expensive. So the long story short, the answer is roughly n log n, so 100 log 100. And really what you want to consider is the time between getting the time interval that you have between getting a new coupon that you have. So the first one, T1 is basically equal to 1. The first one, I'm getting a new coupon. T2 is very likely to be 2, but it could also be 3 or more. But then the last one is the struggler here, that it takes a lot of time to get the 100th coupon. Good. Now, there is also the Dixie Cup. This was in Newman in 1960. But now it's the same thing, but it's not you have more than one child. So one coupon is not enough. Now you have 3 kids, so you have to have 3 coupons for each one of them. Otherwise, they're going to have a fight. So now you can ask the same question. Now, you want to get, say, 2 coupons from each one of them. Another way to look at it is we have urns and balls. And now you have the urns, and you're going to throw balls into the urns. And you want to make sure that you throw them uniformly at random. The balls are the same. And we want to make sure that every urn is going to have at least T balls. So similar problem. And okay, so this was like well studied, and the connection is clear. And also to have multiple coupons is basically the noisy model, that it's not enough just to have 1 copy per coupon because there are some errors, and I want to get at least maybe 5 copies per coupon or per strand in order to have successful decoding. Good. Now we can also say, sure, what happens if you use some code? I mean, I don't necessarily have to have all the oligos that I have. Maybe if I'm going to have 10,000, it's an MDS code, and maybe every 8,000 out of the 10,000 are enough for me. So I said, sure, no problem. So then it's basically the problem of having only K out of the N urns going to be filled with at least T balls. So at least 80 out of the 100 coupons are going to have, say, 3 copies. Good. So there are many known results on this. There are 3 parameters, so K and N. So N is how many coupons we have, or the urns. K is how many I want to reach and to cover, or how many coupons I want to get. And T is how many copies. So if K equal to N, basically I have no code in the oligos. And T equal to 1, we said it's going to be N log N. If K is less than N, then we're in a much better shape here, because I don't need to get all 100 of them. Maybe only 80 is enough, and this is basically the result. If you want to get T copies, then there is another expression for this. When K equal to N, if K is smaller than N, then there is an ugly expression, but it's something which is possible to calculate. And there is also, this is the PIs that you see here. This is if, for example, it is not uniformly at random. So PI tell you the probability to read the ith coupon. And based on the PIs, K, N, and T, there is some expression for the expectation of the number of reads that we need to do. Good. So now we can come back to the problem that we have. I said I have a file, and the file has like, maybe 10,000 coupons. I can encode them using MDS or any other code that I want to have. And then I'm going to have N encoded coupons. Sure, so with this N encoded coupons, now I'm going to read uniformly at random, say. And the main goal is, again, to see what is the required sample size to have successful decoding. Either I do it with expectation, or if I want to say, to calculate the probability. I'm going to read 100,000 reads. What's the success probability to decode my file? Good. So now you can do all the random variables and basically the probabilities to analyze this one. So so we have some random variable that tells you a number of samples until I'm going to be able to decode my file, and assume that I'm going to have some MDS code. And also, we're mostly going to talk about the uniform distribution. So basically, the first part of this work is using most of the existing results, because so far I didn't tell you anything new. It's basically the same problem of the coupon or the Dixie Cup problem. And but if you want to look at it from the coding side, so the first part is basically just to say, check, I'm almost done using previous results. The second one is maybe I have to be more careful here. First of all, what is the best code to use? And is it MDS code or something else? It also depends also on the distribution probability to read each one of the reads that I have. So then it's also a question, which one give you the best result? And also given P, also what is the best code that you have? So this is the random variable. So nu T, did I write it here? Okay. So this is nu T that we have of P and C. This is the random variable that tells you how many samples I need to read until I'm able to decode the file.
Until
So
you-
it's how many coupons I need to get. What?
until you can decode one strand?
Until I can decode everything.
All strands.
All strands, yes. Good. So I think for the sake of time, because this part is mostly previous result and some new results. And how much time can I go over? Now it's 9:30. If I'm having like 15 or 20 minutes, that would be great.
15 minutes is certainly fine.
Okay. Then everything is negotiable, right? I'm Israeli, come on.
How much time can I go over?
Yeah, that's basically the question. Yeah. So 15 minutes overtime from 95.
Why would the non-MDS code be better?
No, it's not. But it's still a question to ask. But so basically, Yuval already mentioned, like, if you're doing that, like, you might as well just use an MDS code. So this is some of the results here. So basically, it's always better to use an MDS code over any other code. Maybe something surprising is that, or not completely surprising, is the uniform distribution is always the best. It's not something that necessarily you can control. But if you add an option to make it non-uniform for the reads, don't do it. Make sure that everything is uniform, you get a better result.
That's how they sell more cereal.
Exactly.
So, before you phrased it as kind of a hard decision or something, like, you want the coverage of K and so on, right?
Yeah.
But let's assume you just go to n log n or some number, right? You're gonna get a profile of how many, and you'll also know that, right? How many you're gonna see, whatever, 100 times, 5 times, and so on, right? And so the error probabilities will change a lot. So
Sure.
it's much more natural to do something probabilistic because, some of those that you have seen a lot of times, you're basically gonna get error-free, right?
Sure.
So, is it clear that using something like an MDS is actually a good?
This is always, like to say, future work. Now we wanted to simplify it. It's the first, basically the first case that we wanted to study. But really to say that, if this one is going to have, I'm going to have as many reads with, say, 10 copies and as many with 8 copies and so on, then I'm also able to decode it. But sure, that's a future work. So there are many open problems here, and I'll mention some at the end. But I'm going to skip. So now this is some other result about the success probability if you want to have at least T copies per coupon. And again, it's going back to what Rudy asked. It's not necessarily the right question to be asked here because maybe there is some distribution. Maybe I'm going to say 20% are going to have 10 copies, another 10% are going to have 8 copies, and so on. All really good questions. I'm skipping all of this for the sake of time because what we're mostly excited about is what they call it the random access problem. So now I don't want to decode the entire file. Maybe the user come and tell me I want to read strand number 15, only strand number 15. So I want to do random access here. So it's the same problem. I start with, say, my 10,000 oligos. I can encode them into, say, 15,000. Now the user come and say, I want to read only strand number 15. And the only thing which I can do is to read out of the 15,000 uniformly at random. Now the question is, what is, again, the expectation of the number of reads until I'm able to decode this strand number 15? It could also be maybe a subset. Maybe say I'm going to want to strand number 1, 3, and 12. But what I'm going to focus about is only the non-practical case of a single strand that you wanted to read. Good. So then the problem is basically the same. Now I have a code. It doesn't have to be an MDS code. It shouldn't be even an MDS code in this case, and we will see why. But I'm having some code. In the K is the 10,000, and you say the 15,000. Now I have a random variable, tau I of C. So that tells me this is the number of reads that I had to do until I'm able to decode strand number 15. And the question is, what will be the expectation of each one of them? Or what is the worst case? I don't want to have one strand expectation X, and the other one is going to be X square or something. So really the main question is to find the expectation for each one of them, and mostly to study the worst case. So the maximum expectation that I can have over all of the oligos that I wanted to read. Sure. So this is basically the problem, and this is what I want to analyze for the next 15 minutes that 10 minutes that I have. Good. So maybe the simple case is I don't use any coding. So I have 10,000 oligos, I store them, I get also 10,000, and then I can ask the simple question. Now, if I want to read strand number 15, so the success probability is going to be 1 over 10,000. So the expectation is going to be exactly 10,000. Sure. Nothing too surprising here. And you can also calculate what the success probability if you're going to read as many oligos. It's a Bernoulli random variable, so it's very, very simple. Sure, but then we know that the expectation is going to be n, or basically it's going to be k, and But what I want to ask is, can I do better than K? Can I use an MDS code or any other code in which the expectation is going to be strictly better than this number that I can do without any coding? So to analyze this, you can see now it's start being more similar to this LRC or code with availability, in which you can have some maybe other ways to decode the oligo that you wanted to read. If I want to read oligo number 15, the strand 15, either I read it itself, or maybe I'm going to read some other oligos, other reads, in which from them I can also decode all strand number 15, and the more recovery sets, the better it is for me. Also take into account, if I'm going to increase the code, then the probability to read each one of the strand is going to be smaller, because if at the beginning I had K, now it's going to be N. So now on one hand, I have more ways to recover every strand, but on the other hand, the probability to read each one of them is going to be smaller. So it's a trade-off which you need to understand. Good. So recovery sets, maybe you've seen like enough in LRC, distributed storage, in any other way. But here I'm talking about the minimal retrieval set. So I have some information bit, we can call it even, and I want to look what are the possible recovery sets that for this bit. So let's start with the simplest case that we have. I have the simple parity code. So this is the 10,000 strand. I'm going to add one more, which is their sum. And now I can ask the same question. I want to read strand number 1. I know it has two minimal recovery sets, either itself or everything together. And now I can ask, is this going to be better than K or not? So before, no coding, we said the expectation is K. Now with coding, I'm going to add one more. So here the probability, the probability is almost as good as before. Now it's a 1 over K plus 1. Before it was 1 over K. But I have another way also to decode the rest, and then I'm also able to decode strand number 1. Who thinks I'm going to do better than K? Who thinks I'm going not better than K? No, depends on K. So the question does not depend on K. So once again, like if you think I'm doing better, this is going to be better than the non-coding one, please raise your hand. What? Little better is better. Who thinks I'm going to do worse? Okay. So 1 or 2 more slides. I'll breathe some tension now. Good. So this is the general result. Basically, say I'm still with n equal to K. So if n equal to K, I'm just going to store everything as is. Don't try to kind of like make other permutations or something with the data. Don't make it worse. So this is when n equal to K, and this is some result on this. But one thing, so to analyze this n equal to K plus 1 or other codes, we have one property, and is to say that if I'm going to have for strand number 1 two mutually disjoint recovery sets, then this is going to be the expectation for the number of reads that I have. So the H here, it's not entropy. This is the harmonic number that we have. Good. So this is one result, and we can plug it. If I'm going to use, and you can also extend it for multiple disjoint recovery sets. But now if I'm going to do the simple parity code, now I'm going to put, so one set, its size is 1, the other one, the size is K. So now I'm going to have H of 1, harmonic number, plus H of K minus H of K plus 1. I got K. So nobody was right, but it was a misleading question. Good, so bummer, like I cannot do, it's like I don't do worse, I don't do better, but I can still ask the question, okay, so is it still possible to do better, less than K? And then we say, sure, so I know that the identity code gives me K, I know that the simple parity also gives me K. What would you do at this point? Which codes do you want to suggest? MDS code? Okay, let's start with an MDS code. Random code we didn't do, but sure. Another good research problem. So if I'm using a non-systematic MDS, this is the worst. Don't do it. So, but this is just to do a check. You're only going to get worse because you want to keep the systematic part. I want to read this trend. Don't make it worse. But if I'm going to use any MDS code, do you think I'm going to do? Who thinks I'm going to do better than K? Okay, I'm doing it with worse. Sure. But is there an MDS code in which I can do better than K? The answer is no. It's always going to be K. So basically any MDS code, and I'll show you the idea of the proof. Any MDS code that you choose, in particular also the simple parity code, you're going to get K. It was kind of like surprising or disappointing at the same time. So we cannot do better than MDS code is not good. Other codes that you want to suggest?
I do like some simple linear combinations. So of like pairwise, just
I'll get to that with the simple one. Sure. But other codes?
LRC codes with a lot of availability.
It depends how many groups you have, so that depends. But if it's just a simple LRC, it's not necessarily good. But let's start with a simple, the first code that you have in any coding book. Hamming code. Hamming code, what do you think we get? Also okay. Okay. So Hamming code is not good. If not the Hamming, I'll do the, yes?
So is the intuition that basically even when you're using MDS code, you need K to decode even other.
Yeah, if you don't read the information one, you need to have at least K.
From the information symbol, we know is K from the non-encoded part.
No, but the probability is going to be less than 1 over K once you're going to increase it. Sure.
And then if you, for an MDS code, then you have to read K.
Yes.
So that's why so far we haven't been able to.
No, but you have more ways. Any K are going to be okay. And you also have the probability that you're going to hit the same information strand, and then you're going to finish before K. So the question why it's exactly K is not clear.
So Eitan,
Yes.
isn't there something like if the code is transitive due to symmetry, then that same point you would get all of them, and that would violate some.
There is some symmetry property, but a few more slides, I think. Anyway, simplex code also gives you K. Also not disappointing. If you take any product code, like say a simple product code that you have one parity for every row, every column, also gives you K. Good. So it's so far we're not in a good shape with having like good codes for this. How do we design these good codes? And in order to find these good codes, now I can transfer everything to work over a matrix. And here I'll give you one example already for a code that is doing better than K. So here's my code. I'm taking 2 bits, x1 and x2, and I'm going to write x1, x2, then I'm going to repeat again x1, x2, and then there's sum. I took the simple parity code, and I just repeat the systematic part twice. If you think about the matrix, here I have the identity, another identity, and now I have the 1, 1. And here the expectation is going to be strictly less than 2. So meaning less than K. And it's good. In a way, you can think about it that I still have the parity code. I'm not going to have this one, but I have higher probability to read x1, x2 over x1 plus x2. And this is why we do it. And now you can think about this problem. Instead of reading like the bits, I'm basically reading columns of the generator matrix, and I want to decode the ith unit vector. And the question is how many columns I need to read until I'm able to read the ith unit vector. Yes. Up to you. I only want to do better than K. If you want to take n to infinity, I'm all good with that.
but you have a limited number of strands you can store, right? So
I'd say application, but we're still in theory here. So let's not worry about the applications.
n is unlimited. Let's say.
Basically, yes.
What is the lower bound in this case, like as you take n to infinity?
I'll get to that. So, yes.
I'm sorry.
Yeah, just curious to know what would be the number if you don't have just curious.
No, if it's just repetition, then it's K. Like this is the no coding part. So it's the success probability is 1 over K, expectation is K.
I guess I'm a little bit confused. I have strands of length 200, right?
Yes.
And
I don't care about the length now because now we just read a S strand.
I'm just trying to make sure I understand the simplest part of what you're. When I say x1, is that a strand?
That's a strand. It's not the 200 or the bit. This is a strand.
Of 200.
Exactly.
So you're saying the first code is just your messages. I have 2 messages of size 200.
I have 2 strands,
And now I'm going to make
5 strands,
5 strands.
2 copies of each, and their sum.
Okay, but and this is doing. So let me ask this question. A moment ago, you told me that adding the sum doesn't help. So what the difference here is not you're still adding the sum. It's just you don't have in your original example you had the same number of sums as letters, and the only
Exactly.
difference here is that you're going to have some sums, but they're going to be
Less frequent.
often.
Exactly.
And the reason why they're less often is the sum is as good as either. It actually plays 2 roles.
Sure. Yes.
Okay.
Yeah. Okay. And we will extend also this one, but I'll see how much time I have. So this is one for general formula that we have. If I'm giving any generator metrics of the code, and you want to calculate the expectation, so we have a closed formula how to do it. And now whatever I'm doing, for example, like with this metric, with the example that I told you, 1.917, so there is a really what you need to count is how many recovery sets you have per size. So this is what this alpha IS means. I'm looking at this ith strand or the ith unit vector, and I'm asking how many recovery sets do I have of this unit vector of size exactly S. Once you have this distribution or this partition of the size of the sets, then you can calculate exactly what would be the expectation. And you can do it, for example, for this code, and that's how you do it this way. You can also do it, say, for the MDS code. So MDS code, I can ask how many recovery sets do I have of size S, which is at least K. Then every set, because it's an MDS code. So every set, N choose S, every set of size exactly S will be a recovery set. But if S is going to be smaller than K, then I need to have that information strand because it has to be a recovery set, and it need to have at least K. And I don't have I have less than K. So it's going to be N minus 1, choose S minus 1, because I'm choosing that information strand plus S minus 1 more out of the remaining N minus 1. You're putting all of this together, and then you get equal to K. So this is a rough idea of the proof. But now another way to do it, and this is going to the symmetries, Henry asked. Another way to say is, okay, I only looked about the unit vector and how many do I need to sample to get the unit vector. But now I can do the same thing over all the columns of the generator matrix. So this is what is tau I tilde of G. And so if I'm taking any metrics over here, and now I'm asking how many columns do I need to read until I'm able to decode this one, this column, or this column, or this column, this one, and this one. So this is this tau I G tilde that I have here. And one of the surprising results that we saw is that if we take the sum of all the expectations here, it's going to be equal to K times N. So this is basically one of the key proofs that we had here. So which now it tells you that if the expectation for each one of them is going to be the same, if basically all the columns are as probable or they have the same number of ways to decode them, then their sum is going to be equal to K times N. But now I have N expectations, which mean that each one of them is going to be equal to K. And that's exactly what we have, for example, in MDS code. In MDS code, all of them are going to have the same expectation. It doesn't matter which column I want to read. Each one of them is going to have the same distribution of recovery set. And if all of them are the same, it means that each one of them should be equal to K because their sum is equal to K times N. That's another alternative proof for the MDS property that we saw, and many other codes that you have. In the simple parity, product code, and many of them actually you get from this result. The question was? I care, but now I extend the definition. So now I talk about all the columns of the generator matrix. So for all of them, I know that the sum is going to be K times N. Now, if everything is symmetric, each one of them is going to be equal to K, in particular the systematic ones.
The systematic ones better is somehow make it unbalanced so that, like...
Sure. So that's like I'm coming to the next, so this is another, okay. Making it unbalanced, it means that I want to take the information part and repeat it more than once. And that's basically what we did in this example here and in general. So in general, you can start with, say, MDS code or any other code that you have. So it has systematic part and redundancy. Now the systematic part you want to repeat many times, and hopefully you're going to do better. And this is the better picture that you have here. What do we see here? The expectation are normalized by K. So I want to see the numbers to be strictly less than 1. So this is expectation normalized by K. This is how many X is how many times I had to repeat the systematic part. And it's a nice result. It depends. This is the rate. Here K equal to 5. And it depends on the value of X and also what rate you're going to work with. So this is going to be rate 1/2, 1/3, and so on. And you can see what will be the expectation normalized by K as a function of X. So it's not that the more you repeat it, the better it is. It's like you got to be careful. And there is some minimum, global minimum over here. And to find what is the global minimum, that's something that we were not able to figure out yet. We have an expression. So this is the expression for the expectation that you have once you have X copies, and it's ugly. But basically to say if I'm using this rate and to find this point, we're not able to know exactly what it is. Yes, sir.
So the result that the average, the whole thing sums to k times n, that's for any linear code?
Any linear code. Good. So now simple codes for this. 2 topics and I'm done. One simple code to do it. And Rick, you mentioned that also. It's like we try to say, I start with information, U1, U3, and 4. And what I'm going to do is only the sum of every 2 consecutive ones. So U1 plus U2, U2 plus 3, and 4 plus 1. So I do it cyclically. This is actually a good code. It was. And then we're able to show that the expectation is going to be 3.83. Strictly less than 4, so it's a good sign. And you can also extend it. So instead of 4 and 8, you do 2k and k. We have some expression, and this is the numbers over here, basically the values. It doesn't give you a very, very good result, but you get to roughly 0.96, I think it was. So times k. So this is one attempt to do another attempt to have a code. And I think I'll just, this is some result about k, smaller values of k I'm going to skip. Bounds. So you mentioned what is the best you can do. No matter what you do, you cannot do better than 1/2. Well, so no matter what code you're going to have, then the expectation is going to be at least k plus 1/2. Whether you're able to achieve it or not, maybe random coding will. So that's one thing. The other thing is to do it with specifically with specific values of n and k. Then you have another expression here that depends basically on the rate. So that's this is bounds on that, and this is some picture of the bound. I think I'll skip this one because I think I went 5 minutes over the overtime that I asked for. Good. So we talk about the DNA storage channel. I told you basically about 2 problems with this the DNA coverage. Either you want to read the entire file, but what we're mostly excited about is I want to read only one of the oligos that we have. And as you also mentioned here, there are many, many interesting problems, and I'm happy to discuss many of them. And before I finish, I'll do what was done also for the quantum. So together with Rawad, Antonia, and also Dave Lanzman, we organize a workshop at the coming IS18 on DNA storage. Olgita is going to be one of the speakers in this workshop, Zohar Yachini, and some 2 more guys from the industry. So it's we really want to make it a sort of a collaboration and to bring the industry into the society and to really understand what are the problems that we need to work on to really help DNA storage, and maybe not just to work on nice theoretical problems which are not going to be useful in practice eventually.
All right, thank you.
What about security? You give your strings for someone to be printed?
One problem at a time. It's clearly interesting, but there are some attempts and some works, but I didn't do anything about security.
Is it more crypto kind of stuff or more?
I think you can do both.
Just curious about what is the kind of state of the industry right now? You know,
I guess you missed the introduction of 1 minute that I had on this. There are some, we can take it off, but in short, there are some companies, some startups who are doing only DNA storage, and they raise money. There are two of the big ones are, one is called Iridia, it's in Carlsbad next to San Diego. The other one is DNA Catalog in Boston. They both raised like over $40 or $50 million. And they do have a prototype. They try to build a DNA storage machine. Twist, which is a synthetic company, they have a big focus also on DNA storage. So basically what I'm saying, there are enough people who spend enough time and money on this. So hopefully it's going to happen.
Thank you.
So the metric you are trying to optimize is the max of the expectations of the TI.
Yes.
I'm just confused. Shouldn't it be expectation of the max?
I want to see, consider worst case. I don't want to have, for example, one.
The max would be larger than max of the expectation.
Then it's the sum of the expectations. I can take it. Because the sum of the expectation of the.
Expectation of max of tau is. Right?
Oh, sure. Not necessarily, because eventually I'm going to say, I want to read strand number 15, and I want to calculate the expectation for this. And I'm doing it for each one of them.
Max of tau could be very large. You know,
Yes.
in a very worst case, right?
So
So
I'm saying
it takes the expected value of the and then maximum over ROI.
That's what I'm saying. That should be the metric, right? Instead of max of the expectations that he's saying.
Maybe we'll take this offline.
I'm just asking.
Okay.
All right, so let's thank Eitan again.